Good afternoon, everyone. This is Sophie Gilbo from ICLR. First of all, I'd like to thank everyone for joining us for today's webinar. We are pleased to welcome Professor David Etkin from York University, who will be presenting an update of hail climatology in Canada. After working for Environment Canada for 28 years, Professor Etkin joined the Disaster and Emergency Management Group at York University in 2005. He has contributed to several national and international natural hazard projects, including the second U.S. National Assessment of Natural Hazards, the IPCC, was principal investigator of the Canadian National Assessment of Natural Hazards, and is past president of the Canadian Risk and Hazards Network. Professor Etkin will be giving a presentation for about 35 minutes today, and we will take the questions after. If you have questions for Professor Etkin during his presentation, please write them into the question box, and I will make sure to ask your questions at the end of the presentation. I'd like to also inform everyone that the slides and the presentations will be available after the webinar on our YouTube channel. And I will now pass it over to Professor Etkin. Thank you.
Okay, thank you very much, Sophie. I hope everybody can hear me okay. So back in the early 1990s, when I worked for Environment Canada, I did a hail climatology for Canada, and I was approached by the ICLR a year or so ago to see if I was interested in doing an update, and I was interested, so that's what this presentation is about. So to begin with, I would just like to review some of the main ingredients that are needed for severe thunderstorms. And severe thunderstorms are what are required for hail to form. So they're basically, you need three things. One is you need instability in the atmosphere. Two is you need wind shear. And three, you need some trigger mechanism or a lifting mechanism that can sort of make it all begin to happen. So just briefly to review instability. So it's a condition in which air will begin, if it gets a little push, it will just continue to rise because it's positively buoyant. And I have a little figure there that just demonstrates it. It really depends upon the temperature and moisture profile, vertical profile in the atmosphere. So when a parcel of air is pushed upward for some reason, it will expand and cool just because the pressure in the atmosphere decreases as you go up. And then it really depends upon the temperature of the air parcel as compared to the air around it. So if it's cooler than the air around it, it'll sink back down to its initial position, and that's not favorable for thunderstorm development. But if it's warmer than the surrounding environmental air, then it will be unstable and it will continue to move upward. And that's what we mean by instability. So instability is supported by two conditions. One is if you have warmth and moisture in the lower levels of the atmosphere. And then at the other end, if you have relatively drier and cooler air in the mid or upper levels of the atmosphere. This is a typical graphic of the lifestyle of an ordinary thunderstorm, which is not a severe thunderstorm that would generate hail, but I just thought I would begin by showing that. To start off with, you have a cumulus kind of cloud development, and you've all quite familiar with these just from looking up at the sky during the summertime. If there's some instability, then that cumulus cloud will develop vertically more and more and more until you can get a thunderstorm forming. Eventually what happens is you get precipitation which forms in the thunderstorm, and as it drops down it cools the air and that kills the updraft, and you end up with a dissipating stage. So that's a normal thunderstorm that would not tend to create hail or tornadoes in the more extreme case. So what you need to happen for a severe thunderstorm is that cool downdraft, that the precipitation is dropping out of the cloud. It has to be shifted so it doesn't kill the updraft. That's the problem. So that's why wind shear becomes important. So by vertical wind shear, there are two kinds. One is where the speed of the wind increases with height in the atmosphere. And you can see the figure in the right-hand side, the two cases. The one on the left side is where the wind is the same at all levels in the atmosphere, and the cloud is just a vertical development. And that's the normal garden variety type of thunderstorm. But then if you have wind shear, say wind's increasing with height, then the thunderstorm tilts. And when it tilts, the precipitation and cold downdraft falls in a different part of the environment, and it doesn't kill the updraft, and that means that the thunderstorm is able to continue to develop. So this wind shear can happen in two ways. One, it can be because of an increase in speed, but it can also happen because of a change in direction of the wind. So both those, either independently or together, are what are needed for a severe thunderstorm. Finally, you need some sort of lifting mechanism, something that is going to trigger this instability within the atmosphere. And there are many different triggering mechanisms. Fronts, which are the boundary between cold air and warmer air, are a very typical lifting mechanism. Especially a cold front, as it sweeps across a region, can be a powerful lifting mechanism, and often cold fronts will generate your most severe storms. It can also happen through dry lines. That more typically happens in the US Southwest, or outflow boundaries from existing storms. It can happen because of upslope flow, and because of this, topography is very important. So as the wind is blowing along, if it hits an upslope due to some hills or a mountain or something like that, that force can act as a trigger to begin the thunderstorm development process. Just generally speaking, a low pressure system. In a low pressure system, the winds swirl and converge inward and towards the middle of the low pressure system. That creates pressure, which makes the air rise upward, and that can act as a trigger. Hot spots on the surface of the earth. So if you have an area, because of whatever the surface of the earth is, perhaps is concrete as compared to maybe vegetation in other areas, that can be a hot spot, and that can act as a trigger mechanism. There's some aspects of jet streams that can act as triggers. So depending on where your jet stream is, the location of it, that can be very important in terms of thunderstorm development. And then there are things called gravity waves that can act as a trigger. An example of a gravity wave, if you throw a pebble into a pond, ripples spread out from where that pebble sinks into the water. And the force that causes the waves to go up and down is gravity. So as one wave peak goes up, gravity will tend to push it down. It's the restoring force. And you get gravity waves in the atmosphere as well, and they can act as triggers for thunderstorms. So if you have all these three things in place, if you have the instability, if you have the lifting mechanism, and if you have the vertical wind shear, then you have the conditions in place for severe thunderstorms, which can result in hail, heavy downpours, strong winds, and sometimes tornadoes. So this is just a graphic of a severe thunderstorm. So on the left side, it's just a cartoon, basically. In this particular one, it shows a severe thunderstorm that does have a tornado attached to it. But most severe thunderstorms don't have tornadoes, but they will have the heavy rain and hail that you see coming down from the center part of that cumulonimbus cloud. So in this particular case, you have all the conditions that are necessary. You have an unstable atmosphere, you have a trigger mechanism, and you have wind shear. And I'm just going to go to pointer options here. So in this area, going up here, you have your updraft, in this case, a rotating updraft, which is, pushing that development of the thunderstorms. And because you have wind shear, you have this precipitation and the downward motion within the atmosphere displaced over from where the updraft is, and therefore that downdraft does not kill the updraft, and the thunderstorm is able to continue to develop. When this rising air gets to the top of the troposphere, which is called the tropopause, and typically that's around, say, 30,000 feet or so at our latitudes, and it hits a stable layer. Up to the tropopause, temperatures decrease with height, but once you get into the stratosphere, temperatures begin to increase with height. And so there's a strong restoring force that occurs at the tropopause. And you do see a little area where the cloud will punch through the tropopause, but basically the cloud tends to spread out and form an anvil in the sort of different directions just under the tropopause. And over on the right-hand side here, you can see a photograph of an anvil. So this is this spreading cloud, which is hit the tropopause. There's a little bit of a penetrating top here, and underneath it is the cumulonimbus cloud. And I just have a couple of pictures. It stopped, the video part stopped. Maybe if I go back to arrow, there we go. So in the middle part here, you can see some time-lapse photography of the thunderstorm developing, and then just at the bottom, I just found a little video of some hail hitting a pool that I thought was kind of neat. In terms of hail formation, this is just a quick little YouTube video of a minute that I thought was a nice little thing to share with you. So I'm just going to go to YouTube and just play this for you.
It takes very special conditions to create a hailstone. You need summer thermals, and you need a violent thunderstorm. Because of the height of thunderclouds, some of the water droplets inside them freeze. But the powerful updrafts created by the warm weather keep the droplets supported in the cloud, where they collect more water, with new layers freezing on in a separate shell. Until finally, there are so many layers that they're too heavy to be supported, and they fall to the ground.
Okay, so just to go to the previous slide, what happens is these particles get caught up in this rising air. Because it's cooler aloft, if they're in liquid form, they'll freeze, and they'll tend to bounce up and down the cloud as they're caught in these updrafts and downdrafts. And every time it goes up and down, another layer of ice will form. And if the updraft is strong enough to keep the hail particle suspended for a long period of time, you can get many layers of ice forming, and you get extremely large hailstones as a result. So why is it we get hail in Canada, and why is it that some areas are more prone to it than others? And that has to do with the geography of Canada. And it's the same for the States, the areas in the States that get severe thunderstorms as well. So if we look at this topographical map of Canada, what we have is an area on the west coast. We have these mountain ranges out on the west coast, and further east we have the plains. And this is the reason why these thunderstorms form. So to begin with, In the lower levels, every now and then you'll get a flow of air coming up from the Gulf of Mexico. That's the air mass source. And this air tends to be very moist and very warm. It's typically maritime tropical air mass. But at the mid and upper levels, the prevailing winds which come from the west start off coming from the Pacific Ocean. It's a cooler air mass. And as this air mass crosses the different layers of mountains out in the west coast, it drops a lot of precipitation. And then by the time it gets to the east of the mountains, it's fairly dry. So what we have is that condition for moist, warm air in the lower levels. You have drier, cool air at the mid and upper levels, which is exactly the condition you need for that instability. Additionally, we have that directional wind shear occurring. So it starts off as perhaps with a southerly component or a southeasterly component at low levels, and it veers to perhaps westerly with a westerly component. And so that shear is favorable for the thunderstorms to develop, because then again, you have that downdraft separated from the updraft, and therefore it doesn't kill the thunderstorm. So if God designed a perfect region for severe thunderstorms to happen, he designed it in North America, east of the mountain chains. So the previous climatology was based on data from 1977 to 1993. It is getting a bit old and long in the teeth, and so for that reason, everybody was interested in seeing if we could update the data, and that's what this was all about. One interesting aspect of hail damage I thought I would share with you is that it seems to have a property called fat tails. And this is characteristic of disaster data sets in general. So whether you're looking at flood damage, tornado damage, hail damage, earthquake disasters, pretty much any set of disaster data tends to have this characteristic of having a fat-tailed statistical distribution. And when you have fat tails, what it means is that the very rare events that are also very high consequence tend to account for quite a bit of the cumulative impacts. So in this particular case, it's not a very large data set, but you can see here there's one event, which was the Calgary hailstorm in 1991. And if you take a look at those 24 events, that one event was 27% of the total cost of all 24 events. I took this from one of the IBC disaster databases. And because of that, any risk analysis done of not just hail, but any disaster data set, it's important to take account of these worst case scenarios. Even though they don't happen very often, they just are so impactful relative to the rest of the events that it's really important to take them into account. So again, this notion of fat tails is one where the frequency of large events fades slowly relative to a narrow tail distribution. And the typical bell curve, for example, that we all had our marks adjusted to when we were in school is an example of a narrow tail distribution. And if you do a literature search, you'll find quite a bit of research supporting the notion that disasters in general suffer from these fat-tailed problems. So it's just a point about disasters in general, but hail in particular, that I just wanted to share with you. There was a study published a few years ago, 2014, flood insurance claims of fat tail getting fatter. If you just Google it, I think you'd be able to find that paper. It's available to the public. And what it did was analyze flood insurance claims in the States and did find that because it's a fat tail getting fatter, it means that the more severe events were becoming increasingly important. And this notion supports the idea that catastrophes are tending to get worse, not better, over time. A discussion of why that happens is a long discussion. We don't have time for it now, but maybe some future webinar might be interesting to pursue. So let's go back to the actual hail climatology. So this particular study was based upon Environment Canada weather stations, and this is just a plot of the locations of Environment Canada stations that have observed hail and that were used in this particular study. We have a data window to work with. So this is a plot showing the number of monthly observations for hail observing stations. And what we found was before about 1977, really hail was not typically observed by very many Environment Canada weather stations. And then there was a change of policy in 1977 where a directive went out saying that observers will record hail observations. And then it was standardly being recorded at all the different weather stations in Canada. Then over time, starting in the mid-90s, the number of weather stations observing hail began to decrease. And after about 2007, really very few stations were observing hail anymore, as there was a transition towards automatic stations and budget cuts to Environment Canada. So really, there's a narrow window of time that we can use to develop hail climatologies based on station observations. So we were restricted from 1977 to 2007. The previous study ended in 93, so this did give us an additional 14 years to look at, but obviously, from 2008 onward, we were not able to use that data because it just wasn't there. I took a look at trends in hail frequencies based at the provincial level. So basically I took all the weather stations or hail observations in a province, and I just averaged it to see what the average hail frequency per year was during the warm seasons of May to September for that province. So if you take a look at this left-hand graph for Ontario, you can see that there really hasn't been much change. If you do a linear regression, you find a very slightward negative slope, which doesn't look to be very significant. So my interpretation of this is between 1977 and 2006 in this particular case. The trend is pretty neutral or very slightly negative in terms of hail frequency. There was one interesting paper published in 2002 that just took a look at severe hail events, whereas I was just looking at hail observations, period. And that particular trend did show a slight upward trend, although if you don't look at data from 1979 to 1982, it looks pretty neutral as well. But that was a different study that was just based on severe hail. If we move westward across the country, say we go to Manitoba, we see something similar to Ontario. There's a very slight negative trend. There's a lot of variability around it. It would be hard to call that statistically significant, but it does show that particular slightly negative trend in hail frequencies. Saskatchewan, very similar to Manitoba. There's a lot of variability. The trend is slightly larger for Saskatchewan, and again, somewhat negative. But interestingly, if we go to Alberta, we find quite a different trend. So again, there's still a lot of variability, but it does show an increasing trend as opposed to a decreasing trend in terms of hail frequency. So again, I want to emphasize the point that I didn't look at little smaller regions, which might be of interest, but I was just averaging data for the whole province. If somebody was interested, they could get hold of the data and look at particular areas of interest. Although again, it would be somewhat frustrating that the data really doesn't go past 2006 or 2007. So what are the patterns that we're seeing in terms of hail frequencies? They're pretty similar to the patterns that have been shown up in previous analyses. The slight trends that we were looking at before of slightly decreasing trends sort of through the prairies and in Ontario, and the increasing trend in Alberta would be reflected in this. So you'd see, those slight differences. But just to briefly go over it, I have 3 charts here. So this is warm months hail frequency. So it's only May to September. And the map on the left is for Western Canada. So you can recognize here's British Columbia out west here. Then we've got Alberta in this area. And it's characterized by some fairly strong areas of high hail frequency. I'll be able to show you a blow-up of this in another slide. But in Western Alberta, just east of the Continental Divide, you see there's a fairly large area here of hail frequency and another maximum further to the north, and a very noticeable one in the mountains of British Columbia out here. I know you can't read the numbers that show the values of the contours, but you will be able to see those on a future slide that I'm going to bring up. So here in the middle map, we have Central Canada. There still seem to be a lot of contours there. The values of the contours tend to be a lot less than out west, but you're still seeing some areas of higher and lesser hail frequencies. And this is mainly as a result of topographic differences. And then finally, towards the right, we have warm months hail frequencies in Eastern Canada. There is an area of higher frequencies up sort of in central Quebec here, central west Quebec. Generally speaking, these values compared to the rest of the country are relatively low. So let's just try, one thing I want to mention, in areas where we have a lot of stations, this objective analysis probably does a pretty decent job of figuring out where the areas of higher hail frequency are and lesser hail frequency. But topography does influence hail formation very strongly. And where we don't have a dense network of observing stations, then certainly what we're seeing is an approximation. So those topographic effects aren't accounted for in this analysis. This is strictly an objective analysis that was done by computer of the data. It does change during the year. So if we just look at Western Canada, for example, which I suppose is an area of most interest. On the left-hand map, we have the hail frequency in May, and on the right-hand map, we have the hail frequency in August. So if we just start looking at the left, to begin with, you see there's this area of strong hail frequencies, very high in the mountains of British Columbia here. But as you transition into August, if you look at the same area, you can see there's still kind of a maximum there, but it's much weaker. If we go into Alberta, we do have a bit of a maximum. There's a bit of a maximum in there, coming down into this area. But it's relatively weak. We're seeing numbers of around 0.5. But as we move into August, this sort of whole emphasis here has changed, and the values have gone up quite a bit throughout this area, and we have a fairly strong maximum in through here, just west of Calgary and Red Deer. If we blow that up a little bit, again, you can see this area on this map I've just pulled up is a blow up of just west of Calgary and Red Deer and Edmonton. So again, here's Calgary, here's Red Deer, and here's Edmonton, and you can see this, I think I'll go to, and you can see there's this maximum of hail frequency throughout this whole area in here. So before I get this, okay, now I want to just pull up some specific figures. Okay, so In the maps on the PowerPoint, we can't sort of zoom in on them, and I'm not sure if you'll be able to in the report that's being distributed by the ICLR. But in the maps that we generated, we're able to display them and blow them up like this to take a look at them in greater detail. So for example, this is warm months hail frequency in Western Canada. So I showed you that before. And if you're, say, interested in what's happening, say, near Calgary, for example, then you can just, take it and blow it up, and you can see exactly where the maximums are relative to the different postal codes and so forth. Here's the same thing for Eastern Canada. So again, I'll blow it up, and let's say we look at southwestern Canada. So here we've got the Toronto area right here, and you can see there's a little bit of a maximum northeast of Toronto, up around the Alberta Highlands, I guess that is. But these values, which are 0.6 and so forth, are really much, much smaller than we're seeing in the Western Canada. So for each of these maps, we use different levels of contours so we could display the patterns. But we had to use much higher contours for Western Canada than we did for East. I should be able to pick out Central. Okay, so here we are for Central Canada. And again, you can see the numbers here. They're somewhat higher than for Eastern Canada. For example, in the Southwest here, because of topographic influences, we do have a 1.6 contour, and that's the highest that we see, although there is a 1.4 contour here west of Winnipeg. But again, these maps are available. The ICLR has them if you want to be able to look at them in greater detail. Now, we did get a request. We got some feedback that the maps were a bit difficult and cumbersome to use for specific locations to try and figure out what's going on. So we put together a searchable Excel database. I think this is it. There we go. So what we did for this was we took the raw hail data, which was observed at the stations. We converted it into a gridded hail data set by latitude and longitude. And in the second sheet here, we have longitude, latitude, and the hail frequency May to September associated with that particular latitude and longitude. So if you want to have a particular location that you're interested in, so what you do is you go to the second sheet, press Shift-Control-R, and a screen pops up where you can input the latitude and longitude. So I'll just say, let's say we're interested in, say, minus 125 degrees longitude, and let's say 55 degrees latitude. And if you click Find Closest, then what it does is it finds the 4 grid points that surround the point that you've just input. So it'll be the 4 closest grid points, and calculates a weighted average based on distance to the grid points for your input location. So you can input a particular location and then get an estimate of the hail frequency for that spot. So in this particular case, the weighted average is about 3.1 days of hail for the warm season. And the 4 surrounding grid points are 3.2, 3.6, 2.5, and 2.6. And you can do this for any location. One thing I want to point out, it doesn't actually check and see if the location is enclosed within the grid points. So I could put in a location of, I don't know, how about England? Say longitude 0, I'll leave it at latitude 55. So if you do that, it will still find the 4 closest grid points, but the actual input location is far, far away from Canada. you have to make sure that you have an input location which is surrounded by 4 grid points. If it's not surrounded by 4 grid points, then you're not going to get the number that you would like to be finding out. Okay, so that's what we did for to create a tool for you that would be more helpful and usable. Now if I can get back to the PowerPoint. Okay. So we just went through the searchable Excel hail database. Future analyses won't be able to rely upon station data anymore. So it's going to have to rely upon things like radar data, lightning data, and satellite data. There are existing climatologies out there that do that. So here's one paper, the top one, radar. This was a place in Europe, I actually forget which country it is now. But they used radar data to determine the climatology of hailstorms. And there are also sort of national and global lightning climatologies that can be used to assist with developing climatologies of severe thunderstorms. And this is on the bottom. This is just one example of a lightning climatology. So that's the direction that future analyses are going to have to go. I didn't talk about climate change this presentation, but I'll just say a couple of words about it. So climate change has the potential to increase severe thunderstorm frequency. There are if we go back to an earlier slide, I'll just go back up to near the beginning, where we talked about the different ingredients needed for severe thunderstorms. One was instability, the second was wind shear, and the third was a lifting mechanism. In terms of instability, the signs from the climate change literature suggest that it will contribute towards more severe thunderstorms. That is, the troposphere will perhaps become more unstable. So thermodynamic instability will be positive for the development of more severe thunderstorms. Wind shear is pretty much an unknown, so that is an important component, but it's pretty unclear as to what's going to happen to the wind shear side of this issue with respect to climate change. So that makes it very difficult to make prognostications about what's going to happen to the frequency of hail in the future. So if wind shear stays, is a similar contributing factor to now, then we might say, okay, we're going to have more severe thunderstorms, perhaps more hailstorms. I'm sure there's still going to be lots of lifting mechanisms around. But if wind shear decreases, that might counterbalance the stability issue. Okay, and that's the end of my presentation. And so if anybody has any questions or comments, I'll be glad to do the best I can with them.
Thank you very much, David, for this great presentation. I'll start with a few questions. We have some on the line, and if everyone else has questions, please write them in the question box, and I'll make sure to ask them. So first of all, you mentioned that there is radar data and lightning data. Is this publicly accessible in Canada? Do you think we'll still be able to collect good hail data with this, or how is this going to work in the future?
I guess it is publicly available. You'd have to approach Environment Canada. So they're the ones who archive the radar data. So it's a lot more complicated computationally and in various other ways to use radar data to develop a hail climatology. So it would be very difficult for anybody to do that who wasn't like a professional meteorologist who was specializing in interpreting hail signals. So it kind of takes the whole realm of developing climatologies further into sort of professional expertise. So to do something like that, you would have, I'm not sure how much the hail data is archived. I haven't been with Environment Canada for quite a few years. So you'd have to have long-term archives of hail, which is a huge amount of data. And if they have them, you could run algorithms to try and determine hail frequencies. Radar hail observations, they have their own issues. And the coverage of radar across Canada is not as extensive as just the weather stations, but it is theoretically possible to do that.
Okay, thank you. We also have a question from Mark Baker on the line. He mentioned that the insurance industry was doing cloud seeding out west back in the 1990s, early 2000s. Did this do anything, and how would it affect the statistics for hail data? And just around that, if you could quickly explain for those unfamiliar with the term what cloud seeding is quickly, that would be great as well.
So with cloud seeding, I'm not sure if it's still going on or not, but anyway, they take airplanes and they fly into clouds, and the idea is to prevent severe hail occurrences by putting in lots of little particles that the hail can start to form around, and you end up with lesser hail frequencies, smaller hail sizes, because you're having more hailstones form, so the moisture is more distributed throughout it. So the idea is to prevent the more severe hail thunderstorms from forming. I haven't looked at the research on this. I know in the past it's been a bit mixed in terms of how successful it is, so I'm really not up to date in that. If it does affect hail, it's probably just the formation of the severe thunderstorms, and I don't think it would affect the database that I have, which was just the formation of any hail. But that's a good question, but also a hard one to answer. I don't think that project would affect this particular data, but maybe, Mark, you were thinking of the increase in hail frequencies out in Alberta, and if it's some way related to this project. I'm really not sure how to answer that question. No
problem. We got a lot of questions too about the searchable hail database that you presented. A lot of people are asking if it's accessible or if it's not going to be accessible. I don't know, Dave, if you made it accessible anywhere. Otherwise, I would just like to tell everyone that we're in the process of updating the ICLR website right now. So if it's not already on there, it will be on there shortly, and would be happy to circulate the link at that point. Yeah. Another question, is there any research to suggest Hail Alley is moving north at the moment?
I don't know the answer to that. I haven't looked at. You mean Hail Alley in the Southwest U.S.?
It says high level Alberta was hit with an unheard of hailstorm last year. So I think it's more
so
Canada.
It makes sense that with a warming climate, the conditions for hailstorms are going to shift as the climatology changes. So to expect hailstorms to be moving farther north, as though, say, the maritime tropical air masses tend to go farther north, is it something very intuitive. And I haven't actually looked at the data or for studies to see if that's been happening, but I would expect that is the sort of thing that would happen as a result of climate change. That the areas that are affected by hailstorms will move northward as the air masses, as the atmosphere warms there during the summertime.
Okay, thank you. Another question on cloud seeding. Do you see cloud seeding leading to more smaller hail, possibly leading to flooding due to accumulating hail clogged storm drains?
Oh my gosh. Well, if I known I was going to get these questions, I would have read up on cloud seeding before the webinar.
No problem. No problem. One person, again, around the database, how current is the data collected that is used in the database? If it is aged, any idea when more current data will be applied?
Well, the data is based on 1977 to 2007, and it's not going to be updated, so it's already a bit old. And it won't be updated because Environment Canada doesn't record hail observations at their weather stations anymore. So basically, that's it. It's based on data that stops in 2006 or 2007, depending what part of the country you're in. Like I say, any update is going to have to rely upon other sorts of databases like radar or lightning.
Do you know if there are any plans for Environment Canada to open these stations again or to start collecting hail data again?
Not as far as I know. I think they've just gone over to automatic stations. It's just been part of a general trend in Environment Canada to deal with budget cuts over the years and a trend towards automation. So I have not heard of any plans for them to start observing hail at stations again, and I doubt very much if that'll happen.
Okay, thank you. Another question on the line. It was mentioned that your research was based on total hail, not just damaging hail. Is it fair to assume that occurrence of damaging hail is proportional to the occurrence of total hail?
Yes, yeah, that would be a fair observation. So,
okay.
I mean, there'd be distributions of hail size and thunderstorms. So this data was for all hail, and damaging hail might be a certain percentage of all hailstorms. Is that going to change in the future? This goes to sort of the fat tail getting fatter issue. Maybe with climate change, that specific percentage or ratio will be different in the future than it is now. But I think would be a good assumption to make.
Okay, thank you. Another question about the report. The updated report indicates hail risk in Fort McMurray has increased significantly since your previous report. Is this due to a change in weather or simply more complete data?
That's I would actually, my intuition tells me that it's because of a change in the weather. But to answer that question, I'd actually have to go back and look at the data because that right now, that's just my feeling. I know in Alberta, we did see increasing hail frequencies over time. So that's why I'm thinking that's the answer. But that was an average for the province. It wasn't at one particular area of the province. So if I was going to answer that question properly, I'd have to go back and look at the area around Fort McMurray and do a trend analysis of that particular sort of region. But I suspect it's been a weather shift.
Okay, thank you. We have another question on the line. Someone that stated an Canadian Underwriting Magazine article that said, in a low probability, worst case scenario, a single major hailstorm in Canada could result in insurance claims of up to $13.5 billion, according to a new research paper from ICLR. What would a storm like that look like?
I'm not sure I understand the question.
I think the person is asking how severe or perhaps how widespread, like how big of a storm would it need to be to reach that level of damage?
Really big? I mean, it would have to be a very bad hailstorm in a worst case location. Otherwise, I'm just not sure how to answer the question. Sorry.
No problem. Hailstorms can vary in size. So hailstones, sorry, not hailstorms. What are some of the factors that affect the size of the hail that hits the ground? And is it possible to predict in advance how severe a hailstorm will be?
Okay, so one of the biggest factors is the strength of the updraft. So you need a strong updraft to keep that hailstone circulating within the storm and continuing to accrete additional layers of ice around it. Severe thunderstorms can have updrafts, I think, in excess of 100 kilometers per hour. So they can be very, very strong. So one component is, how strong that updraft is, and that's a function of the level of instability in the atmosphere. But you also need a lot of moisture. So the amount of moisture within that storm is also an important factor. In terms of predicting it, we certainly have ways of predicting the severity of thunderstorms. Our computer models do it. We can take a look at our upper air soundings and measure things like the lifted index or convective instability, other instability indices like CAPE, and they will give an indication of how severe the thunderstorm will be. But in terms of a particular one in the short term, predicting the size of the hail, that's probably more a question of looking at the radar reflections from that storm and sort of observing the size of the echoes and so forth.
Okay. Thank you very much. I have one last question here. If anyone has other questions on the line, please feel free to write them now in the question box. So the last question I have here is, you mentioned there is currently less data in Canada, and that I think you said in 2007 they stopped collecting hail data. Do you know if there's still data available in the United States, for example, and could that help predict future hail patterns for Canada, or is it too remote to assist with this process?
Oh, that's an interesting question. So I'm really not sure what's happening to the U.S. Observing Network. I haven't looked at it, so I don't know to what extent they're observing hail through their weather stations, or if they've gone the same route as Canada. But in terms of trends of hail, anything that was happening, say, in the northern plains, east of the mountains in the States, I think would also be reflected in what's happening in southern Canada. I mean, it's just a political boundary. So I think any studies of what's happening in the States would be useful indicators of what might be happening in Canada as well.
Okay. Thank you very much. So I see no other questions on the line at the moment. David, do you have any last comments that you'd like to share with the group?
No, thank you for putting up with me and for, I'm sorry there are a few questions that I had trouble addressing because I haven't sort of really looked at those sides of things. But if anybody has any further questions, you can always send me an email and I'll do my best to get back to you.
Perfect. Thank you very much for this very informative presentation, and thanks everyone for joining us today for this webinar. Please join us next month for our next Friday forum. And for those of you that have Family Day, have a great long weekend. Thanks again for joining us, and this concludes the webinar. Thank you.